electric field is the same. What we want to do in chapter 23 is to be able to answer the following question. What if I release an electron at this point, next to this plate? And as you know, an electron is a negatively charged particle, right? Of a certain mass. And what if I release it from rest so that its initial speed is 0? What do you think is going to happen to that electron?
It's going to get pulled towards the positive plane.
It's going to get pulled towards the...
It's going to get pushed by the negative plane towards the positive plane. And
right, so the negatively charged plate is going to repel it, push it to the left, and the positively charged plate is going to attract it. That electron is going to go to the left, right? Another way to see that is the following. What did we say in chapter 21 is the force on a charged particle that's placed in an external electric field?
K, Q1, Q2 for...
No, that's the force between 2 point charges. Q times E. So this is the charge that experiences this force when this charge is placed in this electric field. This electric field is not the electric field generated by this. I call it the external. So when you place the electron over there, it is in someone else's electric field. It's in the electric field of the two plates, of the two charged plates. So the electric field there, the sigma over epsilon naught, is external to this electron. It is not produced. True, the electron produces its own electric field around it, but not at its location. But the electron is in the electric field generated by these two charged plates. And the charge of the electron is some negative number, negative E. I'll just call it negative E. But what is the electric field that the electron is sitting in? Is the electric field generated by the two plates, which is sigma over epsilon naught to the right. Yes? Yes? And this will have a magnitude of E, which is the charge of an electron, 1.6 on 10 to minus 19, times sigma over epsilon naught. But what direction is the negative of to the right?
To the left.
To the left. Okay. So in the way you look at it, this electron is going to go to the left. And it's going to go, by the way, this force is constant, right? Can you see that the magnitude is constant? And the direction is constant? So F equals ma, it'll have a constant acceleration. And what we want to know is, when this electron is released from rest, it's going to experience a force to the left, right? It's going to get pulled this way. An electrical force exerted by the two charged plates, and it's going to go and boom, it's going to hit over here with some speed. How fast is it traveling when it hits that plate? It's really no different from this problem. I have an object. Instead of an electric field that's uniform, it's the gravitational field. Instead of a charge, it's an object with mass. And I let go. With what speed does it hit the floor? So you did that problem in physics 185. So this is sort of equivalent. Right? That was an object moving in a region of space where there is a constant acceleration, resulting because the force on it is constant. Now, this is probably the only problem where a charged particle is going to be moving in a region with uniform electric field. Every other problem, it's going to be changing. And if the electric field is going to have different values at different locations, the resulting force on the charged particle that moves in that electric field is going to be different. So therefore, the force is not going to be constant, and therefore the acceleration of the charged particle is not going to be constant. And therefore, we cannot use the kinematic equations. V final squared equals V initial squared plus 2a delta x. Right? Delta x equals V naught t plus a half. We cannot use those kinematic equations. So for those problems where the resulting acceleration of the charged particle is not constant, we need to solve those problems using the work energy theorem. So what we do in chapter 23 is we now begin to talk about, well, we use the work energy theorem to figure out how fast this charged particle is traveling when it hits this plate. So we have to talk about, well, not gravitational potential energy, but now electrical potential energy. And that's in chapter 23. That's what we do in chapter 23. Now we begin to solve these problems using the work energy theorem. It turns out that these are actually easier problems than the ones you encounter in Physics 185. And it's easier because, well, we consider the motion of these charged particles, but these are always moving in vacuum. So you don't have to consider a normal force. You don't have to consider a force of friction. You don't have to consider a string tied to the thing, pulling on it. You don't have to consider somebody pushing it with a hand, right? So it's just the electrical force. That's it. And we're going to learn about magnetic forces in chapter 27. And it's just going to be, and it turns out that the electrical force is a conservative force. So we associate with the electrical force an electrical potential energy. And we express the work done by the electrical force in terms of a change in electrical potential energy. So the problems turn out to be like the problems that you did in 185, Physics 185, where you just had kinetic energy and gravitational potential energy, and with, you know, just conservation of that energy. That's what we're going to be doing over here. Right? Just conservation of energy. It's not called mechanical energy anymore because the electrical potential energy is not mechanical, so it's just the energy. And we're just going to use, you know, essentially the work energy theorem, which in the end will just be conservation of energy of a charged particle moving in vacuum. Right? So here we have vacuum. Kind of nice because then you don't have to worry about friction, you know, normal forces, a string. Okay. So can I erase this? Okay. Oh, there was another problem, but maybe I'll address that later on. Let me ask you this question. Suppose we have a point charge over here. Let's plus Q. And I ask you, that's it, right? Only that charge and vacuum all everywhere around, right? And I ask you, what is the electric field right here? At a distance r away. What's the electric field? What would you say? You gotta know this answer, right? Because you just took a quiz on this type of thing.
K, Q
The
over R
magnitude is
squared.
K, Q over R squared. And what's the direction? Away from it, right? Because I made this positive, right? Now, what if I ask you this? What's the force right there? What do you say? Depends on what? Depends on what? But I haven't said that there's a charge in there. So what's the answer? There's no force. Right? Remember the F equals QE? Well, the force there on a charge there would be that charge times the electric field there, which is this. So we know the electric field there, but there's no charge over there. So there's no force. It's like if I ask you right here, what's the gravitational force? Right there. Right there, right there. What's the gravitational force? You might think mg. Well, g is the gravitational field of the Earth. That's like the E. But then there's no mass over there to feel that force. So there's no force over there. But there is a gravitational field there. Everywhere in this room and outside, there is a gravitational field. G, downwards, 9.8 meters per second squared, downward. That's the Earth's gravitational field at places close to the surface of the Earth. But there's no force over there because there's nothing over there to feel the force. Now, if I put an object over there with mass m, Now I can ask you what is the force on that. And it would be this mass, that's like the Q, K, F equals Q, E, that's like the Q and F equals Q, E. So it's this mass times the gravitational field over there, which is generated by the Earth. This mass is in an external gravitational field generated by planet Earth. The mass itself generates a gravitational field around it. It's capital G, the mass of it divided by some distance squared, but not at the location of it. So, yes, are we good with that discussion? Yes. So, I cannot talk about a force over there because there's nothing over there to feel the force. But I can talk about an electric field. And if I ask you, at this point right there, you see that point right there? What's the gravitational potential energy? If you remember a gravitational potential energy expression, which one would you remember? Anyone remember any expression for gravitational potential energy? Gravitational potential energy? What would you say? Say it louder.
I don't want to. G.
There are two actually. There are two expressions. If you tell me one of them, you'll make my day.
Isn't it G, big M, or mass of the Earth?
What's that?
Mass times gravity times height.
MGH, correct. But what's the mass over there? There's no mass, so there's no gravitational potential energy over there. I cannot talk about a force over there unless I put a mass over there. And I cannot talk about a gravitational potential energy there because there's no mass over there. So if I place this mass over here, then I can talk about the force on it exerted by planet Earth, and I can describe also that interaction between this mass and the Earth in terms of the gravitational potential energy of this marker when it interacts with the Earth. So it's mgh. The h is the height and m is the mass of this. But if there's no mass in there, there's no gravitational potential energy. So a charge generates something around it. An electric field, which will exert a force on another charge only when that other charge is brought into that electric field. And there's no potential energy over here, electrical potential energy, unless I put another charge in there to interact with this, and instead of talking about the force between them, I can talk about the energy of interaction between them. So, yes?
Yes.
So if I'm talking about forces, it's the force that something exerts on something else. So I have to have in my equation reference to the two things that are interacting with one another. Right? And if I'm talking about energy, it's the energy of interaction between them. It has to do with both of them. So how do we then assign a potential energy over there? Well, I can only talk about a potential energy over there when I put another charge over there. So before I put the other charge over there, it's like I have this. I have this charge and nothing around it. Why would I be interested in an electric field over there? Only if I'm going to put a charge over there and I want the force of that charge. But what if I want the energy of that other charge placed in there? Then I don't use the electric field. I use something else. Like, the MGH, I use the GH, not the M, right? So something that has to do with whatever I place in there. So there's something over here that's labeled V, and it's for a point charge is KQ of R without the square. And it's not a vector, because I'm going to use this to calculate potential energy. And energy is a scalar quantity, not a vector quantity. So this is called electric potential. And it will only be useful if I put another charge over there, and then I want to know the energy of interaction between them. Like if I put a charge, see, if there's no charge over there, I cannot talk about a potential energy over there, and I cannot talk about a force over there. There's no charge to experience the force. There's no other charge interacting with the first charge that I placed there. So I cannot talk about the potential energy, and I cannot talk about the force. Now, if I put another charge over there, then I can ask, what is the force that this charge exerts on that one? Right? And I can also ask, what is the potential energy of that charge as it interacts with this one? Then I can talk about the energy. So if I place a charge over there, I'm going to use green. Let me call it Q prime. Now I can talk about the force on Q prime. Right? And then suppose I make it positive 2. Now I can say that there's going to be a force on that charge in the same direction as the electric field produced over there by this charge. Because that force is going to be Q prime, which is positive, times the electric field there. And the electrical potential energy of interaction, at this point, now we can talk about an energy, electrical potential energy. That will be the charge that I place there, just like Q prime times E gives me the force, but if I take Q prime and I multiply by this V, that gives me the potential energy. And that'll be in joules. You know, the metric system, this is in joules. By the way, this electric potential over here is in, this electric potential is in volts. That's why volts. That's why the V is used.
The Q in the V somewhere, is it a Q or a Q?
No, it's this one. This one produces that V over there. And when I place a charge Q prime over there, the energy of it is Q prime times that V over there, produced by the first one. So the force on that is Q prime. This is the electric field right there, where Q prime is at. And for the energy of this charge, it's actually, as it interacts with this one, it's Q prime times whatever is produced there by this, which is KQ over R. Actually, in this case, this turns out to be Q prime KQ over R. So this is KQ Q prime over R. Remember that in the case of gravitational potential energy, you can write capital G, M1, M2 over R, right? Except that that turns out to be negative, right? This could be positive or negative depending on the charges. If the two charges have the same sign, plus, plus, minus, minus, the energy is going to be positive. But if the two charges have opposite sign, plus and minus, the energy is going to be negative. So this expression is analogous to this. This is gravitational potential energy. This is electrical potential energy. But notice that the expression for the electrical potential energy makes reference to the two charges that are interacting with one another, just as gravitational potential energy makes reference to the two masses that are interacting with one another. But if I do not have a Q prime over here, I can still talk about the electric field there produced by Q, and I can still talk about the electric potential there produced by Q. But I cannot talk, if I don't have Q prime here, I cannot talk about a force over there, and I cannot talk about a potential energy over there. So the difference between V and U is you add the word energy to U. So it's electric potential, energy. And this one is just electric potential without the word energy.
Does electric potential energy have like an analogous word to volts that we might know? So like, we know V in volts.
So this would be joules per coulomb. Like if you saw for V, it would be energy divided by charge. Right?
Okay.
So it would be joules per coulomb. And if, for example, how much time do we have? I think we're supposed to be done, right?
5 minutes.
Okay, let me just finish with this. Suppose I have a charge over here of 3 times 10 to the minus 9 coulombs. 3 nanocoulombs. And I ask you, what is the electric potential here 1 meter away? that would be K Q over R. So that would be 9 times 10 to the 9th times Q, which is 3 times 10 to the minus 9, and R is 1 meter, right? So it gives me what? This cancels this. This gives me 27 over 1. So this will be 27 volts. Right? And if I ask you, okay, go 3 meters away from, the only charge in this problem is this. I mean, it generates an electric potential everywhere around it. It generates an electric field everywhere around it, right? I'm interested in the electric potential now at 2 points. 1 point 1 meter away, and the other point 3 meters away. So what would we get over here? So it would be K Q over R, so that would be 9 times 10 to the 9th. Q is 3 times 10 to the minus 9, and I have to divide by 3. Notice I don't divide by 3 squared, right? Then I will be calculating an electric field. Electric potential doesn't have the square in the denominator. Electric field does have a square.
And then just to be sure, we leave it in meters, right? We don't change it to.
Well, this will be, if you use the charge in coulombs, this is 9 times 10 to the 9th, which is newtons, meters squared per coulomb squared.
Oh, yeah.
This has to be in meters. And this would be what? This cancels that, this cancels that, this would be 9 volts. Now, if I measure the difference in potential here and the potential over there, suppose this is like this, to an oscilloscope. And this is the red one. Oops, I made it blue, but this is red. Remember the alligator clips, right? That cable that you grab the terminals of the battery? And this is the black one. So the oscilloscope measures the difference between those two potentials, and it always measures the potential of the red end minus the potential of the black one. So at the red end, the potential is what? 9 volts. And the potential of the black one is 27 volts. So this will read, what is it? Is it minus 18?
Yeah.
So this difference of two potentials, when you take the difference between, this quantity at some point and that same quantity at some other point, that's the definition of voltage. The voltage is a difference of two potentials. That's why the unit of voltage is also the volts. Because it's a potential in volts minus another potential in volts. So this is the voltage. And that's used for coulombs, but I can think of that as volts.
So why we don't take 27 minus 9?
Oh, you could. It depends on, you could take, if you, like in the lab, I had to measure like the terminal voltage of a battery, but then I had to switch it. So the oscilloscope measures, or the voltmeter always measures the red one minus the black one. So if you switch these two, then the red would be at 27 and the black one at 9, so 27 minus 9, it'll be plus 18 volts. And if you start it from 0, it'll jump up as opposed to jumping down when, So, in chapter 23, we introduced electric potential, and it's something new to you. The nice thing about it is that it's not a vector quantity. Electric potential is a scalar quantity, so you don't say it's away or towards the charge. No, it's just KQ over R. The only way to figure out, this Q over here, you must plug in the sign. If it's plus, it's plus. If it's minus, you gotta put in the minus sign. Right? Because electric potential doesn't have a direction associated with it. Because eventually you multiply that by a charge and that'll give you energy, which is a scalar quantity, not a vector quantity. But the electric field is used to calculate a force, which has a direction, right? And you have a scalar times a vector giving you a vector, so this has to be a vector. So electric fields are vectors with directions, right? Away from the charge if the charge is positive, towards the charge if the charge is negative. Electric potential is KQ over R, right? R is a distance. K is a constant, so it's either plus or minus depending on whether the charge that's producing it is plus or minus. Just a scalar quantity. It's kind of easier. You don't square the denominator, and you don't assign a direction to it. And we're gonna then use the energy argument to show you how easy it is to solve that other problem where the electron is released from rest at the negative plate, and how fast is it traveling when it hits the positive plate. It'll be a piece of cake. You'll enjoy it. So I'll see you, I guess,
Monday.
next Monday. Have a good weekend. Take care.
As well.